Hello, everyone, and welcome to this webinar presented by Chemometic on the subject of automated cell counting of microcarrier cell cultures. Today, I'll be your host, Dr. Carl Aston, field application scientist for Chemometic in the UK, and I'll be joined by our guest, Dr. Pedro Silva Corto, who we've invited as a recognized expert in the field of cell and gene therapy manufacturing. So with that, I'll just take you into the housekeeping notes for today. The presentation will be roughly 30 minutes long, and after the presentation, we will be having a short Q&A session of roughly 10 minutes. If you could please type all of your questions into the Q&A field down below. We'll answer as many of them as we can today, but in the event that we don't get to your question, we'll be sure to be in touch with you via email to make sure that everyone's questions are answered. So in order to give you a brief history of Chemometic as a company, it's a global leading manufacturer in cell counting and cell analysis. And we've been doing this for roughly 20 years, as you can see from the timeline here. Our counters and cell analyzers have gone through several different iterations over that time. But we like to pride ourselves on developing and producing high precision equipment that delivers consistent data for thousands of customers across biotech, pharma, and academic segments, for applications within multiple disciplines, including cell therapy, virus, and antibody production. Our patented technology ensures our instruments support our customers in achieving exceptional results again and again, while being easy to use. Designed and manufactured and tested in Denmark, our instruments are handcrafted by experts using quality materials. So with that brief history in mind, I'd like to now pass over to Pedro to begin his presentation. I hope you enjoy.
Thank you so much for the introduction, Cal. As Carl mentioned, my name is Pedro. I'm a postdoc here at UCL, and I've been working on the cell and gene therapy field for close to 7 years now. So this webinar today will be focused on the topic of automated cell counting on microcarrier culture, and it was conducted using the nuclear counter NC202 from Chemometic. So before we jump into any data sets, I believe it is important to understand why we should dedicate some time to understand how automated cell counting methods work, especially for adherent cell-based culture. So adherent cells, by definition, require a surface or a matrix in order to provide the surface effectively for the cells to survive and proliferate. So fibroblasts, macrophages, or mesenchymal stromal cells are some of the most common adherent cell types used in the cell and gene therapy space. So typically, your very traditional cell counting protocols for adherent cells traditionally rely on some form of detachment reagent, so typically trypsin or triple E, that has the function to dissociate the cells from the surface that they're attached to in order to generate a single cell suspension that can then be analyzed. So once the cells have been detached, you can then proceed to perform a cell count, and this can be performed manually using the hMSCs, for example, or any automated options like the NC202. But also here at UCL, we have had experience with other instruments from the Chemometic family. We have tried the NC3000 initially before we moved into the 202, and there's also some activity using the NC200. So if you think about the how to expand these cells to large numbers, which is one of the main goals of scalable manufacturing studies, one of the typical solutions or approaches involves using microcarriers, which are small beads up to 200 micrometers that offer a surface for the cells to attach to. So once the cells are attached, they can then be expanded in suspension. And you can see a very good example of that in the image in front of you, so the one that sits at the middle. So it's a spinner flask that goes up to 100 milliliter scale that we used to expand mesenchymal stromal cells. So this strategy that we just described can be used at small scale, and it can go as low as 10 milliliters, but can also be scaled up to the multi-liter scale bioreactor. Successful examples of this have been demonstrated in biotech many years ago with adherent show and adherent hack that then became suspension adapted. But going back to the difficult challenge of expanding adherent cells at scale, one of the key challenges really when conducting this type of studies is how to really perform an accurate and representative cell count of the population you have inside of, let's say, your bioreactors. So today we will share with you our approach to validate a counting methodology using the NC202 from hMSCs. So when we adopted the NC202 and wanted to implement a process to determine cell concentration or cell concentrations of adherent cells, these were some of the questions we tried to answer. So technically speaking, the counting procedure that you'll see today that we used in this work involves two steps. One step is when the count is performed with the cells and microcarriers and the lysis buffer, which gives you an indication of the total cell number in your sample, followed by another count, this one using just the cells and the microcarriers, that gives you an information about the dead cell levels or dead cell concentration. Obviously, by difference, you can then obtain the viable cell concentration. So regarding the study steps that you see in front of you, so the way they were designed and the idea was really to understand how long the incubation time between cells and microcarriers and this lysis buffer had to be in order to get a representative cell measurement, and whether, for example, increasing this incubation time would lead to different viable cell concentration and viability levels. Also, we try to investigate whether operating at different concentrations would give different results. So, and here we were trying to assess effectively the linearity of the system regarding total live and dead cell concentration. And ultimately, we tried to validate this approach that we established to not only real case scenarios, so scenarios that you would expect in a real life, really manufacturing scenario, but also how robust was this protocol that we developed if you think about using other types of microcarrier preparations. So to answer these questions, we came up with 4 different studies that we will now present to you. The first study involved expanding human mesenchymal stromal cells and spherical microcarriers, which are microcarriers that are made of plastic and then coated with collagen, and expand them for 7 days under agitation of 30 RPMs. What we then did 7 days after was to harvest the culture, so the cell and microcarrier mixture, and perform several cell counts and viability determination studies. Here, our goal was to try to establish an incubation time between our cell to microcarrier preparation and the lysis buffer. So what we've done in this study 1 was to incubate the cells and microcarriers with the lysis buffer for 1, 3, or 5 minutes. The first parameter that we assessed was the total cell concentration. And you can see here that irrespective of the concentration that you are operating at, the total cell concentration does not really change if you go from 1 to 3 to 5 minutes of incubation with lysis 1. One trend that we started to note here and started to emerge is that the more diluted your sample is, and therefore less events are being captured, the higher the coefficient of variation is. And this we hypothesized that was related to the fact that we were getting closer to the lower level kind of recommended lower level of detection for total cell concentration. Obviously, we applied the exact same strategy and exact same principle to viable cell concentration, and we obtained very similar results. So across a wide different range of concentration, it didn't seem to impact too much, going from 1 to 3 to 5 minutes in terms of the incubation between cells, microcarriers, and the lysis buffer. So we were confident at this stage that irrespective of the time that we were going to move forward with in terms of cell and lysis 1 incubation, we would be fairly confident that we would get very similar results regarding total cell concentration and viable cell concentration. We obviously applied the same strategy to dead cell concentration values, and you could see here that the answer was exactly the same. So it didn't really impact too much, going from 1 to 3 to 5 minutes regarding the incubation with lysis 1, because the dead cell concentration in this case was comparable across incubation times, really. So here we were in full confidence that irrespective of the time, incubation time that we wanted to move forward with, we would feel very comfortable that we would still get the exact same result, which does indicate the robustness of the counting methodology using the lysis buffer, and obviously within this time incubation time study. We also tried to assess the impact of incubation or different times of incubation on cell viability, because we were trying to understand whether exposing the cells to lysis 1 for longer would cause a detrimental impact on cell viability, but this was not verified. As a matter of fact, and as you can see here, given the fact that these values were statistically similar, what this indicates is going from 1 minute to 5 minutes does not lead to a detrimental impact in cell viability. So obviously from our perspective, and at this point, we were fully sold on moving forward with 1 minute incubation time, because obviously, given that there's no difference in total, viable, and dead cell concentration and viability, we really wanted to do the measurement as quick as possible. So we decided to move forward with the 1 minute incubation time. So the second study, which pretty much identical to the first study, so the same type of cells, the same microcarrier, the same seeding density, the same expansion time. And here, what we were really trying to understand is whether within a reasonable concentration range, whether the equipment, obviously across these different parameters that we assessed before, had a linear response. And this is exactly what you can see in front of you. So on day 7 of culture, we harvested the total cell population, and we created this dilution series effectively to try to again test the linearity of the equipment. And you can see here 2 main findings of this study effectively. So if you look at the left, you can see this R² value when we run a linear model across a different concentration does come well above 0.9, which strongly indicates that this is indeed a linear model. So if you look to the right-hand side of the slide, you can see that when you factor in the dilution to effectively try to get a feel for the real cell concentration, or the linearized cell concentration, I should say, we observe that the higher the dilution factor is, the larger the standard deviations were. So this we hypothesized at this stage that was related to the fact that we were getting to that lower threshold recommended for cell measurement. Obviously, we then applied the exact same strategy for viable cell concentration, and you can see that linearity in this case was also verified. Again, this is demonstrated by the R-squared value when we ran a linear model. Again, the linearized values show exactly the same trend. So all these concentrations are statistically similar as we expect when we linearize them. And the closer we get to that lower cell threshold, the larger the standard deviation values are. Then again, we ran the same approach for the dead cell concentration. And here, perhaps it is important to highlight that we were operating below the lower kind of limit recommended for the equipment. And as you can see here, perhaps this is why it results in a perhaps less linear response when we applied a linear model to the dead cell concentration. Again, this is most likely, we suspect, because we're operating with very, very few events. So in order to try to understand whether we would have any deviations here on the viability, so again, we try to dilute the sample 1:1:4 and concentrating it to kind of capture that wide range. And here, essentially, what we were trying to assess was not necessarily linearity, because obviously when you dilute the sample or you concentrate it, you would not expect that the cell viability would change. And here, that's exactly what we were trying to assess, was whether performing or counting cells at a different concentration, whether this would give us different viability levels. Then we would have had a problem, but this is not the case. So it didn't really matter how concentrated the sample was or how diluted it was. The cell viability levels were exactly the same, which again gives us full confidence that the protocol was, robust enough within this concentration range. We then move forward to a real case study. So what we tried to do past this point was to expand these cells, again using the exact same methods, but using two different microcarrier formulations. You can see here that we expanded the cells in spherical microcarriers and in Cytodex-1 that are represented here in the graph in front of you in green and red respectively. The main outcomes here of this study was that our protocol, which included the lysis-1 buffer and 1 minute incubation time, was robust to detect cell concentration and cell concentration changes over time across two different microcarriers. Here on the experiment itself, you can see that the cell counts that had a smaller CV, so coefficient of variance, happen between day 4 and day 6, so effectively the exponential growth phase. And larger coefficient of variances happen toward kind of the late stage of the culture. So here we hypothesize that because of microcarrier to cell, cell to microcarrier bridging, so effectively when the cells are growing attached to the microcarriers, they will start to bridge with one another, which then creates microcarrier to cell clumps. And then obviously this creates different culture conditions and perhaps impact on the coefficient of variance that you would obtain. So here, this is perhaps more a limitation of the culture system itself, rather than the counting methodology per se. obviously, we analyze the viable cell concentration as well. And you can appreciate how small some of these coefficient of variances are. So in most instances, we are operating below the 10% level, which is fantastic and quite honestly unachievable if you do manual based counts. Again, our counting protocol was robust enough to demonstrate that past day 5, using the spherical microcarriers, we didn't really observe any cell growth. But in this in the cytodex series, really represented in red, the cells keep growing until day 7, and eventually, after 7 days, both of these microcarriers led to the exact same cell concentration. Obviously, we evaluated the response of the dead cell concentration variable as well, and we didn't see, any meaningful differences over time. However, and if you remember what we just saw on the graph before, past day 5 in the spherical series, the cells did stop growing. But we didn't see here a correlation with the dead cell concentration, which means that perhaps that kind of dead cell and necrotic processes and apoptotic processes have not quite yet just started. So here are the viability levels associated to this 7-day culture, and this is perhaps one of the most interesting kind of findings that we obtained in the study, and that were beautifully captured by the protocol that we developed and by the NC202 in this case, is that you can see that during these 2 days, so that goes from day 0 to day 2, there's a drop in viability. And then this viability picks up. So this is really reassuring that the equipment and the protocol established managed to capture a very well described phenomena in the microcarrier based culture, which is the difficulty of the cells to adhere to microcarriers during those 2 initial days. So as you can imagine, when you seed cells and microcarriers, this is a process that is not 100% efficient. So some of these cells will die because for multiple reasons they cannot attach to the microcarriers. And it is also always to expect some cell death level when you are trying to promote effectively or to establish the so-called attachment phase of cells with microcarriers. And we can see here that the equipment and the protocol established really captured this in a very very clear manner. You can see that there's a clear viability drop, and if you look at the red series, so the cytodex one, and then an increase of that viability, and the same to a lesser extent when we use spherical microcarriers. So at this stage, we were convinced of several elements or several things that the protocol could deliver. So we were convinced or sold on the fact that 1-minute incubation was sufficient to generate accurate cell concentrations, and by cell concentrations I mean total cell concentration, viable cell concentration, and dead cell concentration, and also that the current protocol was sufficient to capture culture changes that we would expect in microcarrier to cell-based culture, like the initial viability drop during the attachment phase. We then went on trying to evaluate how robust was our protocol and the NC202 when we started to think outside of the box and decided to go for other different types of microcarrier formulations. And this is the experiment design that we put forward at this stage. So instead of using spinner flasks, we decided to go for ultra low attachment plates. So basically, these plates were treated to prevent cell attachment to the bottom, and we incubated or seeded the cells with different types of microcarrier formulations in these ultra low attachment plates. So effectively, we tried to use a scaled down model for microcarrier culture. And then we tried various different microcarrier different formulations, and we run a battery of several analytics. Obviously, cell count and viability determination using the NC202, but also other forms of assessment that we typically run in our lab. So indirect cell concentration measurements, metabolite concentration, and this is related to the fact that mammalian cells do break down glucose into lactate, for example, during glycolysis, and also evaluated how the cultures look like, so their morphology under phase contrast microscopy. Starting here with the imaging information, you can see that so these blue dots here really represent cells or cell agglomerates. Exception made here with this helix 2. So what happens with helix is that if you have a phenol based medium, so a medium that looks red, what happens when you seed ilex to this culture, ilex 2? So this microcarrier, for reasons that we do not know, absorbs all the culture, which then kind of switches the colors when you're trying to do imaging, and this is the sole purpose. But across the sole reason as to why this image here looks different, but across all the other images, you can see that irrespective of the microcarrier type, we managed to successfully expand cells across all of them. And we're talking about cytodex, spherical, even ilex, plastic plus, and glass. So here, the question became, what is the better microcarrier, or the best microcarrier here for us? So the one that maximizes cell concentration. And this was what we tried to answer with the analytics that we run after, because that's obviously the key limitation of microscopy and imaging in general. So in the left-hand side, you have the results of the absorbance values generated when we measure indirect cell concentration. So here we use this reagent called WST1 from Roche that effectively breaks down a salt in the culture medium, and you can then measure the absorbance, and depending the absorbance levels, you can then infer the levels of expansion or cell concentration. Obviously, this doesn't translate to absolute values, but this is particularly useful when you have different groups, so it's relative to each other. But irrespective of that, you see that after 7 days, cytodex 1 and spherical emerge as the best performing groups here, if you look at the left-hand side. So when you look at the right-hand side, and this was again performed with the NC202 from Chemomatic, the message is clearly the same. So cytodex 1 and spherical also emerge as the best performers. We have ilex 2, plastic and plastic low, slightly below this, and all the other options obviously and clearly not as good. So here at this stage, we had two different analytical techniques. So a proliferation assay, so using the WST1 reagent, and the NC202, giving exactly the same indication effectively. We tried to then evaluate or confirm this with additional analytics. And this was when we tried to measure metabolic species such as glucose, lactate, and ammonia, if you look at the right-hand side. So here, and perhaps we focus on the left first, we can see here that Cytodex and spherical led to the lower levels of glucose left in the medium after the 7-day expansion period. What does this mean? Means that the cells consumed nearly all the glucose available, obviously, and inversely related. You can see that this is why Cytodex 1 and spherical also led to the highest levels of lactate, because, as I mentioned, glucose breakdown leads to lactate formation in mammalian cells following glycolysis. So on the right-hand side, we were then trying to evaluate ammonia concentration and its buildup in the culture, given that this metabolic species is also typically measured because of the catabolism of glutamine. So during the process of expansion, cells use glutamine and convert it in ammonia during amino acid synthesis, really. And again, when you look at ammonia concentration, the groups where the highest buildup levels were reported were Cytodex and spherical 1. Cytodex 1 and spherical. So here, and we're looking at 4 different analytical techniques. All of those demonstrated that those 2 particular microcarriers were the ones that that maximized effectively cell growth. And this was reassuring that we had established a robust protocol to measure cells attached to microcarriers using the NC202, and the trends that this protocol kind of demonstrated or led to were validated by other independent analytical methods as well. Here, just to conclude, we'll finalize shortly after this conclusion slide. So we demonstrated that we can use the NC202 to determine cell concentrations of mesenchymal stem cells attached to microcarriers. We then went on demonstrating that we can use as little as 1 minute of incubation time with lysis 1 to determine the cell concentration effectively. We then demonstrated that if you look at total cell concentration and viable cell concentration within a wide range of concentrations, the response is expected to be linear. We then applied this strategy to different microcarrier preparations, and we demonstrated that the counting methodology is robust across different conditions, different microcarrier preparations, and probably most important, is accurate to detect real phenomena that happens in microcarrier cell-based culture, things like the viability loss during the attachment phase. And with that, I would like to conclude, and I'm happy to take any questions from this point onwards.
Okay, that was great. Thank you very much, Pedro, for a very in-depth and knowledgeable presentation. I can already see we've had a lot of questions from before the registration, when the registration period started, and we've been getting a lot of questions during the presentation itself, so people want answers. I'll just remind everyone who's listening that we will get to your questions in time. If we don't get to them during the course of this Q&A session, we will follow up by email afterwards. As such, if you want to keep adding questions to the Q&A down below, we'll make sure we get to them. So let's begin. I've picked out a few questions. Some of them are a bit high level, some of them are a bit more in depth, but I'll start with quite a high level one, which is, what do you think was the most challenging aspect of counting cells in microcarrier suspensions using the NC202?
Yeah, it's a very interesting question. Yeah, I'm forced to say, really, there's really not huge challenges involved. So it's surprising how straightforward the technology works. Really, the only details that you know entail or are included in technologies, you have to do 2 counts, and as you saw in the presentation, a 1 minute incubation time, and there you go. And then you have your viable total dead cell concentration levels and the viability. So it's really straightforward, and that's why we decided to adopt routinely here in the lab, not only just for microcarrier based culture, but also for suspension based, really.
Okay, great. It's good to hear you're having such a good time with the instrument. As a follow-up question to that, do you think that this method that you've developed is applicable to both small and large-scale experiments?
Yeah, absolutely. So you could the technology itself, it's really agnostic to the how large your expansion technology is, right? So we've used things from well plates, as you've seen in the presentation, up to the multi-milliliter scale. So we were operating at the 100-milliliter scale. But obviously, more recent studies, we conducted multi-liter scale bioreactors with microcarriers, and the technology performs the same. So really, it's completely agnostic, so you can adopt it for different scales that you may have in the lab.
Okay, that's great. So that's great to hear about the instrument. But if we move on to more details about the assay itself, what made you really hone in on the Spherodex beads as kind of the best representation, the best option for your experiment, really?
Yeah, so in the beginning, when you start thinking about microcarrier culture and scalable expansion, really, when you think about microcarriers, they come in so many different sizes and also charges and also coatings. It really becomes difficult to identify from the get-go which the best performing kind of agents may be. So we knew that the spherical microcarriers were manufactured with polystyrene and then coated with collagen. And then there's a wide body of literature that suggests that coating surfaces with collagen in general, not just microcarriers, but coating surfaces with collagen and fibronectin as well, typically leads to enhanced cell attachment and therefore proliferation. So really the main reason behind us choosing spherical was because of that collagen coated element that the microcarriers do have.
Okay. And I suppose that shows with, on one of your slides, you showed that at the first couple of days when you seed the microcarriers, there does seem to be some difficulty with attachment between microcarrier types. Do you think that that could work as a detriment, whereas the attachment is too strong and you can't lyse them away from the carrier itself?
That is absolutely the case. Perhaps not for spherical based microcarriers, but it is a very well described phenomena for microcarriers, for example, like Cytodex 1. So one of the main challenges of using Cytodex with some cell types is that the type of attachment is so strong that actually harvesting, not just performing the count, because the count you can always do, because I think the technology is robust enough to work with a wide range of microcarriers. But when you think about really physically detaching the cells from the microcarriers, using Cytodex 1 in particular is particularly difficult. So that's definitely the case. So the way that we try to go about that is, if we have to use Cytodex, typically the exposure between cell microcarrier and an enzyme that actually performs that detachment typically needs to be longer.
Okay, that makes sense. It also links into another question we've had. Why lyse the cells and not just disassociate them from the microcarriers with, say, trypsin?
Yeah, so it's a much longer procedure. If you think about using trypsin, then to have a accurate representation, you probably want to filter the cells and the microcarriers out. So there are several kind of steps that are included, right? So effectively, when you use something like the NC202, it's a much simpler and much faster approach providing you're looking after a value for the cell concentration. Obviously, if you want physical detachment, you still have to use those methods, which then again, you have to first trypsinize the cells, so you separate the cells from microcarriers physically, but then you have to filter out the microcarriers that they are, roughly 10 times larger than MSCs. So MSCs in this case are 20 micrometers. These microcarriers are around 200. So you can separate them by size using a filtration step. So it's a much longer process effectively. And obviously time costs money. And that's why for routine operations and on a day-to-day basis, when we do not need a full harvest of the vessel, we run a cell counting step really.
Okay. So it's an efficiency and therefore more of a cost-effective standpoint,
Absolutely.
I guess.
Yeah.
Excellent. Okay. And you've done these experiments using mesenchymal cells, which is great. But have you tried to validate this particular protocol with other cell types?
Yeah, we've done. So we've done with these primarily isolated MSCs. So we also validated with immortalized MSCs carrying a telomerase gene, but also with fibroblasts. So we tried these effectively 3 different cell types. But we believe, the protocol and the technology is most likely robust enough for any other adherent cell type that you may encounter, really.
Okay, that makes sense. So you mentioned earlier in your presentation that you considered using the NC3000 for this particular process. What was the logic behind going with the NC202 in the end?
Yeah, so we are huge fans. We have to admit here at UCL with the NC3000 because can do so many different assays. But from what I remember, and please correct me if I'm wrong. So the NC3000 and the way the protocol for counting cells attached to microcarriers includes effectively two type of solutions.
Yes.
And the protocol itself and the way the algorithm works takes slightly longer. So the NC202 is much more straightforward, much faster. So that's in the end why we decided to move to the 202, and so far we didn't regret that decision. It has been working very well for us, really.
Well, that's great to hear. For those of you that don't know, the NC3000 also works on a slide-based technology. So with the 202, you'll just be using cassettes. Yeah, so a much more simple kind of plug in and go sort of process. Okay, well, I can see we're coming close to the end of time for the question session. So I'll just ask this last one, but I would encourage everyone listening to keep answering, to keep asking questions in the option below. We'll make sure that we get to all of them via email afterwards, and it will be either myself or Pedro answering them. It really depends on the context of the question. As you can appreciate, we have different specialities and expertises in these areas. So I'll just answer this last question before we finish the session. The question I have is, you displayed a difference in CVs throughout the graphs that you were showing. And although there was a general minimal impact, do you think that you are still able to trust the low concentration and the higher CVs that you're seeing in those experiments?
Yeah, so that's a really great question. So we believe, and I believe that we went through the presentation, but so the closer you get to that kind of lower recommended limit for cell concentration, really that's when the coefficient of variance starts becoming larger than expected, sometimes above 20%. So the way we take it, and obviously we don't know the ins and outs of the algorithm. But what we assume is that, and we've seen also in the presentation, is that between those recommended cell concentrations, the response is going to be linear. So this is what we demonstrated. Outside of that range, what we assume is that possibly the response of the algorithm is no longer linear. So any deviations to the real cell concentration maybe, so you don't really know for sure if you're overestimating or underestimating the cell number. But in any case, we would be cautious to adopt those values. but we assume that it wouldn't be too far off. But perhaps it really is no longer linear outside at the optimal range, I would say.
If I might add to that from a chemometric perspective, the range we give for each of our instruments is absolutely, as you say, we've validated it within that range to be linear, to be as accurate as we can make it. The fact of the matter is you get down to a certain low concentration and you encounter not only limitations in the instrument, but also limitations in the statistics of those particular counts. So I'm sure you can appreciate that the fewer events that you're counting, the less robust the experiment is. So we would completely agree with you in the conclusions you've drawn there. Okay, well, as we've reached the end of the session, it just leaves me to thank you very much again, Pedro, for coming along and giving your presentation today. It was super informative, very, very interesting, especially from our perspective. Everyone who's listening, thank you very much for coming along. As I say, I encourage you to still keep adding your questions to the Q&A options we have here, and we will get back to you as soon as we can with answers by email. So thank you very much. And goodbye.
Thank you.